Okay, welcome to part 3. In part 2, we discuss the subsets of real numbers, and we discussed that the natural numbers are subsets of the whole numbers, which are subsets of the integers. And the integers are the positive and negative whole numbers. So if you think about at this time all of the numbers that were around at this time, this is not enough numbers to discuss the entire number system. We needed something else, and if you just think about what are all the numbers between 0 and 1. Well, there's infinitely many numbers between 0 and 1, but the main number is like, what's 1/2? That's what really comes to my mind when you think what's between 0 and 1. That's a half. But there's also a third. There's also a fourth. Okay, so we needed another set of numbers to describe everything that's going on here. And that set of numbers is called the rational numbers, which is what we're going to start with this lecture here. So the rational numbers. And the rational numbers, they're defined by the capital letter Q. And I'm going to use set builder notation to define the rational numbers. So the rational numbers are any set of numbers P divided by Q. So any number of the form, any ratio of the P and Q where P and Q are integers. So P and Q are integers. And from the first lecture, what do we learn from the first lecture? Part 1. What must not be true here? Q should not be 0. Q should not be 0. We can't divide by 0. So there's no instance where Q is 0 in this place. But Q can be 1. So what happens if Q is 1? Well, if Q is 1, then P belongs to Z. Right? If Q is 1, then P divided by 1 is P, and P and Q are integers. So this tells us that Z is this. Well, let me write it over here. Z is a subset of Q. Z is a subset of Q because if Q is 1, then P is an integer, right? 50 divided by 1 is 50. Negative 50 divided by 1 is 50. Both of those are integers, so every integer is a rational number. So now we have another situation here because we already know from yesterday or the last lecture that W is a subset of Z and N is a subset of W. So now we have that N is a subset of W, which is a subset of Z, which is a subset of Q. Alright, but there's other things we need to learn about Q which separate it from other numbers. What happens when Q is not 1? Well, we have two types of decimals. And we actually have really one type. But to make everybody happy, well, we're going to call them two types. The first type is where the numbers, the decimals repeat in numerical form. I used to call this, when I taught math, how to keep an idiot busy. How do you keep an idiot busy? You do 1 divided by 3. All right, 1 divided by 3. And I'll be honest, I haven't really quite figured out the division by decimals, how that works with addition. One day I'll sit it out and figure it out, but we're going to have to do long division on this. So this means we're going to take the denominator and divide it into the numerator. And this is what I used to call how to keep an idiot busy. Okay, well 3 goes into 10. And if you recall, dividing by decimals, you move the decimal point up. And 3 goes into 10 3 times. 3 times 3 is 9. We subtract, we get 1. Bring down a 0. Look, we're back at 10 again. 3 goes into 10 3 times. 3 times 3 is 9. 10 minus 9 is 1. And you can see that this will infinitely go on. So we can say that 1/3 is equal to 0.33. And you could either put ... or we could use what's called a repetend. And a repetend is a bar on top of the digits that indicates repeating pattern. So if I say, I know that these 3's are going to go on forever and ever and ever, I can just say that 1/3 is equal to 0.33 bar. 0.33 bar. And this is the first type of decimal. Decimal that repeats. And of rational type. Okay, so the first is repeats. The second type is terminates. But really, the digits that terminate also repeat, and I'll explain in a minute. For example, 1/2, which is the easiest of all. Okay, 1/2 if I take 2 and I divide it into 1.00. Okay, where you bring the decimal up, and 2 goes into 10 5 times, and 5 times 2 is 10, and 10 minus 10 is 0. Okay, so it terminates. But it really repeats zeros. So they really all repeat, but it terminates, because repeating zeros doesn't really mean a lot, doesn't really add a lot, but all rational numbers repeat a pattern forever. Okay. But if it repeats a 0, we say it terminates. Okay. So rational numbers in decimal form either repeat a pattern indefinitely, or terminate. So now, in the last few minutes, we're going to introduce the last subset of the real numbers. And we already discussed that N is a subset of W, which is a subset of Z, which is a subset of Q. Now, this is the last part of numbers. We thought we had it all figured out until I'm not sure the time frame on this, but it's much after these numbers were discovered. We're talking centuries after. There's another kind of number. opposite of rational is irrational. Irrational. And those digits do not terminate. So in decimal form, they do not terminate and they do not repeat. And there's people out there that memorize digits of irrational numbers. Mainly, the most famous irrational numbers, of course, is pi. Pi is irrational. If you look at pi in decimal form, the digits never terminate and they never repeat. But you could point to pi because it's real. E. E is probably one of the most famous numbers as far as math goes, because E, and until, I don't want to jump ahead, I'm just going to say that E and pi are the two most favorite irrational numbers. E and pi. And then any non-perfect root. And what I mean by non-perfect is like the square root of 4 is a perfect root because the square root of 4 is 2, but the square root of 5 is not perfect because the square root of 5 doesn't have a number that's an integer that multiplies by itself to be 4. So the square root of 5 is irrational. In decimal form, the square root of 5 never stops and never repeats a pattern. Ever. And they've taken pi out to billions and billions of digits, and they have yet to see anything repeat. And I don't think they ever will, because it's irrational. It's a completely different pattern. And there's savants out there that memorize these, and Guinness Book of World Records. If you ever see, when I was a kid, we actually saw the Guinness Book of World Records. I haven't seen one in years. I guess it's all online now, but there's people that can recite and memorize this number out to tens of thousands of digits, and that's what they do. There's a contest, and they can just go rattle them all out. And I don't know if that's really. I don't think that memorizing all these numbers is really contributing to mathematics, but if it makes you feel better, then good on you. Pi is approximately, and we have to use approximately when we discuss pi, because I could never, ever, ever write all the digits of pi in my entire lifetime. Okay, because it keeps going and going on. We say pi is approximately 3.14, and we say that E, which we'll talk about later, is 2.71. And this number is very popular in compound interest and growth formulas. And we'll get, E is very special in calculus. When we get that far, we're not that far yet. So, okay, we have this irrational number. All right. So we need to really discuss our strategy of subsets of real numbers, and after this we can get on to other topics. So, we started with the natural numbers. They're subsets of whole numbers, which are subsets of integers, which are subsets of rational numbers. And then we have irrational numbers, and it's the irrational numbers, and because these two are not the same, and the irrational numbers, it's the rational numbers and the irrational numbers that make up the real numbers. And what makes these numbers special, this is probably all the numbers you've ever known so far, because, well, all right, is they can all be graphed and they can all live in a coordinate system. Let's just say here. All right, 1, 2, 3, 4. They can all be visualized because they are real. Okay? They're real. This is what we call a coordinate system, where I can plot rational numbers. So we could say that this rational number, which is real, is 1/2. It lives right here. E, I said that E was approximately 2.71, and it lives approximately here. Now, yeah, I'll never, ever, ever be able to pinpoint that location on the map here. This is E. But I could get a pretty close proximity that E is right around 2.71. Same with pi. Pi is approximately 3.14. So I can say that pi is right around here. And then we're going to later learn that what makes real numbers special is that we can compare them using greater than, less than, and greater than. And this is greater than. So I can say that E is greater than 1/2 because I can visualize it. I can say that pi is greater than E. And we're going to talk about this in more detail in the next lecture. I appreciate your time. If you need some tutoring help, contact me on Facebook. And until part 4, we'll see you then. Thanks for watching.